This is the second video in section 10.1, the ellipse. In this section, I want to take another look about another quality of the ellipse. On top of the foci, the vertices, the major and minor axes, all these things we've seen already, I want to talk about the eccentricity of an ellipse. Okay. This is a very accurate wording here, this description. It says the degree of the elongation of the ellipse is measured by the eccentricity, we label it E, of the ellipse. So we're saying the more elongated looking the ellipse is, the bigger the eccentricity is going to be. And the more perfectly perfectly round, I should say, the more similar to a perfect circle it is, the lower the eccentricity is. We can say that's not very eccentric, right? It's a pretty simple shape if it's not elongated in one direction. So if we have an ellipse defined by these equations we've seen already, we say the eccentricity E is given by the distance from the center to a focus divided by the distance from the center to a vertex. And in these formulas, A and B are positive, C is positive, and we have that nice formula to remember, C squared equals A squared minus B squared. And so if you think about how this has to happen, if you've got your ellipse, right, if your focus is out here, that's a distance C back to the center. Well, the distance out to your vertex, that's a distance A. And since this C value is always to this focus that's always inside of the ellipse, right? It's never out here. Then that tells us C is always less than A. So that means this ratio here, if C is less than A, that means that ratio is always less than 1. And since all these numbers are positive, that's going to tell us that this eccentricity, C divided by A, is also a positive number. So it's really just a number between 0 and 1 that measures how elongated the ellipse is. Something very close to 1 approaches an infinitely thin and infinitely long ellipse as we get closer and closer to an eccentricity of 1. As we get closer to an eccentricity of 0, that becomes more and more like a circle, where the So let's see. Right, because that would have a distance C equals 0 from the origin, which means this focus has retreated from both sides back to the center and become a perfect circle again. Okay, so this is just the wording of that description I've given. Let's determine the eccentricity of each of these ellipses. This is not going to be very difficult. Remember here, the bigger number is A squared. The lesser number is B squared. And we know C squared is A squared minus B squared, which in this case gives us, it looks like, 216. Right, 216 for us. So if we are looking at this number, we might want to figure out what is C. So 216. It's not a perfect square, but let's see how we can chop it up. Maybe we divide it by 4, and that leaves behind 54. So we divide it by 4 again. That's 4 times 4 times... that actually doesn't divide. 9 times 6. There's its factorization. We can see what will come out of this root. A 2 from the 4, a 3 from the 9. 2 and 3 outside the root come to 6 root 6. Okay. So that's our C value. Since A was 225, we know A squared was 225, we know A is 15. So we get the eccentricity pretty easily is the C value divided by the A value, which is this. That's an exact value. We could simplify 6 and 15. Have some factors, have a common 3 factor in common. So it looks like I'm getting off to the side here. Let me actually plug this into a calculator so you can see roughly what this equals. 2 times the square root of 6 divided by 5, that equals a very high number, close to 1. Pretty big number, right? That's very close to 1. This is a very eccentric ellipse, right? Which kind of makes sense from the picture here. We're being shown this thing. It looks pretty eccentric, pretty elongated. So this one over here, let's do this. Maybe pause and see if you can work this one out real quick. Same exact idea, the next one here. A squared is 9, B squared is 4, so C squared is 9 minus 4 is 5. C is root 5. So then, since A is 3, we get the eccentricity equals root 5 over 3. And let me plug this in just so we get a sense of how big this number is. Root 5 divided by 3 is about 0.75. That's rounded, but that's roughly what it is. So we notice a lot further from 1 here means this ellipse is a lot less elongated. Okay. Now let's use that to solve one of these similar problems to what we saw earlier, where we have a couple pieces of this ellipse, piece of information about this ellipse given to us, but we want to come up with a standard equation from that. Right away, I'm picking out what I know. The eccentricity here is C divided by A, and that's 3 over 4. Do not mistake this for saying that C is 3 and A is 4. That's not necessarily the case. We're saying C divided by A is 3 divided by 4. They have the same ratio. That's all we're saying there. So if that's the ratio, that means 2C equals 3A. That's all we know from this fact. That's all the eccentricity tells us. It's the ratio of C to A. So let's write the standard form of the equation of the ellipse with these vertices. That's enough to give us a lot of information. So maybe think of a little sketch real quick. Negative 6, 7. 1, 2, 3, 4, 5, 6, 7. Somewhere up here. And 2, 7. Somewhere up here. Those are the vertices, right? So we know this thing's going to look something like this. It's a horizontal major axis, since the vertices lie on the major axis. From that, we can actually figure out where the center of this thing lives. Right? It's halfway between the vertices along that major axis. So halfway between negative 6 and 2 at a height of 7. Well, what is that? Negative 6 plus 2 divided by 2. You average those coordinates to see what's directly in between them. Add them up and divide by how many you have. That's the average of those two coordinates. This looks like that's negative 4 over 2 is negative 2. So the location of this center point here, let's see that. That location of that center point right there should be negative 2, 7. And so right away there we know our H and K. It's those center point coordinates. Keep in mind from this little picture that I've drawn over here, we also know that A equals the distance from the center out to either one of these vertices. Now you could do a little math there or just look at it and count units. That's going to be 4. Right? A is 4 units from the center out to each vertex. So we know A, we know H and K. Keep in mind, what I'm trying to fill out is this this standard form equation of the ellipse. I chose this form where I put the A under the X stuff because I have a horizontal major axis meaning I have a bigger number under the x than the y. So I know my h and k, I know my a value. The last little piece I don't know, I need my b value. But keep in mind over here, because we know the a value, we also know the c value. A is 4. So c, it looks like, is 6. Right. But this is nice. We know c squared equals a squared minus b squared. So that gives us c is 6, a is 4, a is 4. And so we can solve now for the b squared value. Did I make a mistake here? What did I get? Let me see what I've done here. Oops. I see where I made a mistake. Here I made a mistake. I had the eccentricity was 3 over 4. I wrote it as 3 over 2. That's no good. That's 3 over 4 there. I knew something was wrong because I got a bigger c value than my a value. And earlier we said up somewhere else, we said that c is always less than a. So I knew something was wrong. So I double checked and found I miscopied that 4 as a 2 down here. Let's just keep it as this to fix it up. Notice we didn't use that eccentricity to find a, so we're still good there. But when we find c, we have to be a little more careful. C is 3. So instead of 6, I'll write 3 squared here. C is 3. And now we're in good shape. Now if you solve for b squared, you get this, so b is root 7. Or b squared is 7. So we can write our equation. Final answer. X minus h is negative 2, so minus a negative makes plus 2 over a squared. A squared is 16, because a is 4. Plus y minus the y coordinate of the center is 7. Over b squared, well, our b squared value is 7. So that's it. That's our standard form equation of this ellipse. Not too bad. Let's finish up with one more problem. Excuse me. One more problem down here, a nice application of ellipses. These conic sections are used all the time in the study of planetary motion. It's kind of how we understand planetary motion, is through these sorts of shapes. So it's not uncommon at all to see a problem sort of like this. It might be kind of a, that's actually not too unrealistic, but it might be kind of a toy problem, but this stuff is really based on reality. The way these objects orbit each other is nicely describable by conic sections. So let's look at this problem. The comet, I will not try to pronounce this comet, Hyakutake, like just did after saying I wasn't going to try. Who knows how it's pronounced? The comet follows an elliptical path through the solar system. So here's our comet. It follows this ellipse through our solar system and back out. So that's looks like a high eccentricity, right? That's a very elongated ellipse. So this thing comes in, follows that elliptical path through the solar system with the sun way over here somewhere, very close to one of these foci. Or at the focus. It's actually at the focus. But that's going to be very close to where this thing whips around at its vertex of this ellipse and starts heading back out of the solar system. So it says the comet's closest approach to the sun, which is called perihelion, is 0.23019 astronomical units, AUs. That's this many miles if we care about it. It's approximately the distance between the Earth and the sun. It's a pretty standard measure for these big distances in solar systems. And we are given also that the eccentricity of this comet's orbit is this number here, very close to 1, right? Which makes sense with what we expect. It's a very elongated ellipse, so very close to 1 in eccentricity. We're asked to find the distance from the comet to the sun at the point where it's farthest away. So we're told that at perihelion, the comet is 0.23019 astronomical units away from the sun. That's when it swings around at its closest approach. Somewhere way back over here, it turns around, right? The comet comes through, turns around, heads back out. Somewhere way out here, it turns around again, right? And comes back into the solar system. So way close in here is the sun. And as we come around the sun, we are told that shortest distance there. That's our 0.23 astronomical units that was described, this number. We are being asked to figure out how far is this thing at the opposite end of its orbit. So we found out where it is, how far it is from the sun at this orbit. We want to figure out how far from the sun when we're at this end of the orbit, the furthest distance, which we call aphelion. Okay. So remember, we're told that the sun is at a focus. So maybe I redraw, oops, let's not scribble through it. The sun is at a focus. So maybe I redraw this or think about this more nicely put together picture over here to get some information. We know this distance, right? We know this 0.23 ... whatever astronomical units. So what is that value? We know, we know that this 0.23, that's the distance between here and here, right? Between here and here, between the sun and the comet at perihelion. Okay. We also know that the eccentricity, which is c divided by a, equals this number. Right, so let's just work with it and call it E, and at the end we'll plug in this 0.99 mess at the end. But keep in mind, all we're saying here is we know what a minus c is. Right? A is the distance from the center out to this point P. Well, the distance from C to S, that is the distance to a focus. That's our little c. So you go all the way out, A units, then subtract off these C units, you're left just with A minus C in here. So the A minus C quantity, that is the distance of perihelion. That's this 0.23019 astronomical units. Well, keep in mind, that lets us actually solve for, say, C, for example. Or we could say it this way. Solve for A, maybe. No, I'm going to solve for C. Sorry. C equals A minus this number. And just solving for C. And we can plug that back in over here. C is A minus 0.23019 over A. And what else do we know? Well, we know the eccentricity, right? So we know this eccentricity's value. If I can solve for A in terms of that, I can plug in a number for that and find A. So let's see if I can do this. I'm going to split this fraction up. I'm going to write this as A over A minus this 0.23019 over A. And now notice A over A is just 1. Kind of a long problem here. I will isolate that fraction itself. Check my work here. That fraction itself is going to equal 1 minus the eccentricity. Well, I'm trying to solve for A, so maybe I take a reciprocal now. And finally, I can solve for A. 0.23019 times 1 over 1 minus e. Right? This was nice. I know the eccentricity, so I can plug that in now. Plug all this into a calculator, and I get that A approximately equals, let me actually calculate. Right, this eccentricity we said is, that's the weird number, 0.999784. And so when I run all these numbers, then this is what I get. Let's see, I get, this is what I get. I get that A is roughly 1065.7. You might be asking, well, what does that represent? What are the units of this number? A, remember, is a distance measured in this picture up here. And the distances all in this problem are described in terms of astronomical units. So this is a number of AUs. But keep in mind, that's just telling us how far from the center out to each vertex. That's what our A value in the equation of an ellipse represents. And if we look, the picture's gotten muddied up, so I'm going to kind of clean it up over here. If we look, we want to figure out the distance from aphelion, the aphelion point, back to the sun that's at a focus. So that's this distance from A to the center. That's distance A, from the vertex to the center is a distance A, plus the distance from the center to a focus, which is C. That's why this total distance here is denoted A plus C. Well, we're in good shape now. We know what A is. From that, you can figure out what A plus C is. It's the value of A plus, remember, C is just A minus this 0.23019. So instead of C, I'll write what this is. Right, this is the distance we want. A plus C, which is A plus A minus 0.23019, which is just 2A minus 0.23019. And now I'm just going to plug in the value of A up here. The distance approximately equals, let me compute this, 2 times 1065.7 minus 0.23019 equals, I get this distance, 2131, roughly 0.2 astronomical units. So if an astronomical unit is roughly the distance between the Earth and the Sun, we're saying this comet extends out 2,000, well over 2,000 times that far from the Sun before swinging back. Pretty nice little problem here. Let's see. I think I said that was going to be the last one. I was mistaken. I have a couple more I want to go through here. Let's run through here. Running track, as we run through here. A running track is designed in the shape of an ellipse, 100 meters long by 50 meters wide. Use a coordinate system with the origin at the center of the track and a horizontal major axis to write an equation for the ellipse. So we want to set up a coordinate system around this. Major axis should be along the x, we said, and our major axis is the long one. So I set it up like this. That's how we have to have our coordinate system set up. We know this ellipse is 100 meters long by 50 meters wide. Well, that just means that's from here to here is 100. So this is 50 and negative 50. Likewise, from here to here is 50, meaning this is 25, and this is negative 25. Well, with this information, we know A is 50, and B, B is going to be 25. So we're in good shape. We can just write this thing down. It's centered at the origin, so it's not even a shifted ellipse. Let's just write down this equation. X squared over, we do have this distance this distance from the origin out to our vertices in the x direction. It's 50, so it's 50 squared here. Similar for the y, 25 squared equals 1. We can work this out. I think 25 squared is 625. Check my math on that. But pretty easy problem, especially compared to the previous one. Right, the picture gives it all away here. If we think of these equations in terms of how they directly relate to the picture. The a squared and the b squared down here tell us how far from the origin we go to the edge of the ellipse in each of these x and y directions. Okay, this is getting back to solving nonlinear systems. It's a nice tie-in. Let's solve this system. Yeah, I can say honestly, this is the last one I want to go through. Let's solve this system really quick. It's well set up for substitution, right? We already know what y equals. Let's just plug that into the previous equation and solve. And maybe it's useful to look at this picture of the graph of these two shapes and notice we expect two solutions because there are two intersection points. So plugging the second equation into the first one, I get something pretty easy to handle. X squared over 16 plus 4x squared over 8 equals 1. Now to get rid of the fractions here, I'd rather just right now clear them out by multiplying by the LCD, which is 16. And I have to multiply on both sides to balance the equation, but I think that'll clean things up nicely. I think this is what we get. Be very careful here. I distributed the 16 to the x squared over 16. 16's canceled, left in x squared. But I also distributed this way over here. The 16 and the 8 and the 4 all combine to make an 8 here attached to the x squared. On the other side, 16 is more obvious. So we add it up. Single x squared plus 8x squared is 9x squared. That must equal 16. Divide off the 9, and don't forget the plus or minus. Plus or minus 4/3. And that's believable from our picture, right? This looks like the 4/3 mark in the x direction. Right, here's 1, 4/3 to here. From 0 out to here, it looks believable. Likewise in the other direction. Here's from here this way. Okay, so we found the x values. Now we just plug back into this initial equation we used for the substitution to find the y values that go with. Well, let's see, the y values are 2 times the x values. So that's plus or minus 8/3. Is that believable? A little less than 3? Yeah, that's believable. That's a little less than 3 in size. So we know that when x is negative 4/3, y is negative 8/3, and when x is positive 4/3, y is positive 8/3. So we have our solutions. There we have it. Okay, so that is it for this section. I hope breaking it up into 2 videos was useful here. It's quite a bit to it, but it's a nice introduction to conic sections. In the next video, we'll see even more of these types of shapes. Not ellipses, but hyperbolas and parabolas. That's coming up next.